Okay, so now having given a brief curtain raiser on what is possible using, if one decides to compute with quantum bits, let us try to understand the physics and the mathematical structure of these quantum bits better, right? That's what we'll be doing over the course of the next few lectures, probably the next 2 weeks. Today's lecture in particular, I'd like to focus on understanding the structure of quantum states. And in particular, we'll focus on qubits and introduce a geometrical picture of the qubit via something called the block sphere. Okay. And the reference for what we're going to do over the next few lectures is all going to be uh, Nielsen and Chuang chapter 2, right? That will be my primary reference for what we're going to do. Okay, so we said when I defined the qubit, I sort of introduced it in two ways. I said that it is an object that belongs to a two-dimensional linear vector space. Okay, so it's a vector in a vector space, and in particular a complex linear vector space. Okay, and the other way of looking at it is that it is the state of a two-level quantum system. So let us try to understand this aspect better. And of course, they're both related to each other. And the way we'll try to understand this is by reviewing some of the basic postulates of quantum mechanics. Some of you already have prior exposure to this, but maybe many of you don't. So I will go over the I'll go over it in as much detail as we require for this course, right? I'm not going to, this is not a quantum mechanics course, so obviously I will not be teaching you a lot of stuff, material which gets covered in a regular quantum mechanics course. I will not even mention, but I will dwell on certain aspects which might not be covered in a regular quantum mechanics course, okay? Right, so we start, so the aim of the next few lectures will be to go over some of the postulates, the so-called postulates of quantum mechanics. Pedagogically, there are different ways that people like to teach quantum theory, and the way we are going to adopt is what you can think of as a kind of axiomatic approach, where we describe certain axioms on which the theory is based, right? And these are axioms both physical and mathematical, as we will see, right? So the first postulate that I want to discuss is, so what does one mean by postulates of quantum mechanics, right? So this is, like I said, one approach to teaching quantum mechanics is via these postulates. So typically, okay, this is a brief spiel for those of you who haven't seen a course, in formal course in quantum mechanics. So let's just say classically, one typically describes the state of a system So this is a recap, so to speak, or a way to set the stage for the first postulate. So one describes the state of a system using a set of, so those of you who have done courses will call these as generalized coordinates and generalized momenta or velocities. But one can just say that one describes the state of a system using a collection of, let's say, position coordinates and momentum coordinates. Right? The standard example is your billiards ball or a set of billiards balls, if you will. How do you describe at any given time the state of the system is described by describing the set of positions, coordinates of these collection of balls and their velocities or momenta, right? So this description, of course, had to be discarded when once quantum mechanics came into the picture, that there exist systems where you cannot simultaneously describe position and momenta, and then one saw with atomic and subatomic systems various novel features which then told us that this cannot be a description of all physical systems in general. It's only classical systems, systems which do not exhibit quantum behavior, that can be described like this. So how does one describe the state of a system quantum mechanically? And that's what the first postulate tells us. So postulate 1 says that states of a quantum system are associated with unit vectors in a Hilbert space. Okay, and the rest of this lecture we'll try to parse this statement in different ways. We'll try to understand this. Right, so this is a complete departure from what one is used to in classical mechanics or classical theories, where essentially a certain set of coordinates describe the system for you at a given time, and then there are equations of motion there are once you identify the forces within and without the system, once you identify the energy relations of the system, you can write down equations of motion, and you can talk about how the state of the system evolves from one time to the other, right? But this picture was shown to be true only in some limit eventually, and if you want to describe fundamental particles, then you have to go down to describing them in the language of quantum mechanics, right? And quantum theory says that the states of a system are not such collections of position and momenta, nor are they functions of position and momenta, but they are actually vectors in a certain kind of linear vector space called a Hilbert space. And what is more, they are unit vectors in a Hilbert space, right? Okay, so some of you may have done linear algebra courses where the idea of a Hilbert space is introduced for you. For our purposes, since we will essentially be working with finite dimensional systems, we will not be really interested in defining a Hilbert space formally, right? So for our purposes, it suffices to say that, so we in this course at least will focus only on finite dimensional systems. So you can think of this as, in finite dimensions, this is essentially a linear vector space which is endowed with an inner product. So in the finite dimensional case, these are what are called inner product spaces. Okay, and I'll define some of this shortly. So any finite dimensional inner product space is a Hilbert space. If you want to talk in infinite dimensions, then you have to bring into question, you have to be careful about things like convergence and so on. So in infinite dimensions, one has to worry about issues of convergence, issues of completeness, which, like I said, we will not dwell upon in this course at all, but I will just mention this here for those of you who would like to go and read up more about it, right? So in the most general definition of a Hilbert space is an inner product space where every Cauchy sequence, so I have to define for you what a Cauchy sequence is and so on, but I'm not going to do that, but just for completeness, I've written this down in my notes, which I will post, but it's basically that every Cauchy sequence in the space converges with respect to the norm defined on the inner product space. Okay, this is for hardcore linear algebra aficionados here. But the rest of us need not worry about it. We'll just think of this for now as finite dimensional linear vector spaces. Okay, So let's try to understand this better. So what are the properties of linear vector spaces that we will need to recall? Okay. So let me say V is a linear vector space. So this is a bold V. Okay. So how do I want to define a linear vector space? So I will say that it's a collection of vectors, or to be more formal, it's a set of vectors. And I will denote this set of vectors as ket V, right? I can put a subscript Vi to enumerate them and so on, but it's understood that this V is some label which is labeling the elements of this set, right? The ket, as always, for me denotes a vector in a vector space, right? So it's some collection of vectors such that the following properties are satisfied, okay? So first, the sum of two vectors is also an element of the vector space. So let me just formally write this down quickly. So if V and W belong to V, then this sum also belongs to V, right? If lambda, so we also say that this is a vector space on some field, okay? And in this case, we are concerned with complex linear vector spaces. So we will say that it's a vector space on the field of complex numbers, okay? So C denotes the field of complex numbers. So if lambda is some complex number, we call these as scalars, right? To contrast them with a vector. So lambda is some scalar, right? Then lambda times V also belongs to V, right? So more generally, I can combine 1 and 2 to say that if alpha and beta are two complex scalars, right? Then and V and W, so are two elements of the vector space, then alpha V plus beta W is also an element of the vector space, right? And this is the property that we repeatedly invoked when we were looking at superpositions in the last week's lectures, that we made such linear combinations of qubit states, and we said that is also a valid state of the qubit, and that essentially comes from this underlying property of the linear vector space, that if I have two vectors in the vector space, their sum belongs to the vector space. Any complex number times the vector is also an element of the vector space, and therefore any complex linear combination of a pair of vectors is also an element of the vector space, right? Now, this pretty much summarizes what I need to know about a linear vector space, right? So I can talk about, okay, so I can talk about there exists so-called null vector, right? This is sometimes denoted as phi, if you will, such that any vector added to that gives you the same vector, right? So with these properties, we can pretty much define a linear vector space. And like I said, it has to be defined over some field, right? Over some field. So when I said re-bits and all that, right? Real bits, real quantum bits. In that case, the field that one is talking about is simply the field of real numbers, right? In which case, all these properties, lambda will not be a complex scalar, it will be a real number. Alpha, beta will be real scalars and so on, right? So what defines a vector space for you is a collection of vectors which satisfy these properties and a field over which they are defined, right? So let's quickly look at some examples of this to make this idea more concrete, right? And then I will define an inner product for you, which is what comes next, okay? So what are some examples of linear vector spaces? So the first and the most useful example for us is the space of, let me say, the space of D cross 1 complex matrices. Okay, so another way of saying this is the space of D-dimensional complex vectors, right? These are indeed the D-dimensional column vectors. So we saw a glimpse of this again last week when we represented the qubits in terms of these column vectors, right? At that time, we represented them using 2 cross 1 column vectors, right? So now I'm talking about the space of D cross 1, right? So what am I talking? So this space is what is called C with a D on top, right? And I will often use this notation. So the C, the bold C denotes complex field, right? This field of complex numbers. And when I put a dimension D on top, that tells me what is the size of these column vectors that I'm constructing out of this field, right? So this basically means that the elements of my vector space are of this form, right? They are of this form where there's one column and D rows, right? So there are D rows, and so this is called a column vector of D dimensions with complex entries, right? The first thing you notice is that any such vector, right, can be described in terms of D complex numbers, right? So one needs D complex numbers to describe this vector, right? So let me say that I call these D complex numbers as V1, V2, etc., V sub D, right? So what I'm saying is I populate these entries as V1, V2, etc. Okay. I can equally well represent this as V1 times the vector with a single 1 here and B minus 1 zeros plus V2 times 0 in the first location, 1 in the second entry, and all other zeros. Okay. V3 times 0, 0, 1, whole bunch of zeros after that, all the way up to VD 0, 0, 0, 1, right? Where all other entries are 0 except the last entry, which is 1, right? So this naturally leads to the idea of a basis for the vector space. So what is a basis? A basis is any set of vectors, and I will call typically basis using the letter E, that's a standard mathematical notation as well. So let me say E1, E2, etc. And how many of these basis vectors do we have for this space? How many such vectors do we have here? D of them. Good. So let me say E sub D. Okay. So any set of vectors that spans the space forms a basis. Okay, what does span mean? Span means that I can write any element of the vector space can be written as sum over I, some complex coefficient Ci times EI, right? And in the case of this example that we just saw, there are D such vectors EI, right? And in some sense, the dimensionality of the space is related to how many elements you have in the basis, right? So we'll formalize this slightly once we discuss inner product and orthogonality and all that. But for now, we note that every vector in the space can be written in terms of some basic set of vectors. And you have them superposed with these complex coefficients, right? And if you recall, what we did with the qubit was essentially identify the logical 0 and the logical 1, or the bit 0 and the bit 1 of the qubit space. We associated it with two such basis vectors, right? That was a two-dimensional complex linear space. So we had just two such vectors which were required to describe every other vector in the space, right? Okay, so this is one simple example, the space of D-dimensional complex column vectors, right? Another example that one can think of is, so let me just do a few more examples of vector spaces and then I will talk about inner product, because some of these vector spaces we'll also be using in the course of this course. Any questions so far? Okay, so the second example that I want to talk about is the space of 2 cross 2 complex matrices. The reason I want to talk about this example is to give you this idea that to kind of get used to the idea that the idea of a vector space is not restricted to the kind of vectors that we know from three-dimensional coordinate systems and so on, right? That is where we seek our inspiration or motivation from, but really it can be any abstract object, right? Any abstract object can form a vector space with these desired properties. Of course, I leave it to you to check that it satisfies all these properties. If I take two complex d-dimensional vectors, their sum is also a complex d-column vector, etc. Okay, so I leave it to you to check the properties that I wrote down, that there exists a null vector. Okay, so all of these you please check. But the next thing will be a slightly more interesting and non-trivial example. This is often denoted as bold M with a subscript 2 cross 2 to indicate that it's a 2 cross 2 matrix. The mathematicians will also put in a C here to say that, again, it's over the complex field. Okay. So what do I mean by this? So this is the space of, so consider one matrix M of this form, A, B, C, D, right? This is a 2 cross 2 matrix whose entries are all complex. Okay. So of course, again, it's easy for you to check that it's a vector space, that it's a linear vector space. Okay, LVS is short for linear vector space. Okay, I'm not going to keep writing it. But now the interesting question is, what is a basis for this space? Can you guys think about that? Okay, first of all, a related question would be, what really is the dimension of this space? Sorry, say that again.
It's 4, right?
What is 4? The dimension. Yes, indeed,
Yes.
exactly. So the dimensionality of this space is 4. And why do you say that?
Because you can take, so you can put A1 and the rest of them 0, B1, and so basically you can take 4 matrices and generate the entire LVS.
Very nice. Yes, indeed. So I can consider this set of 4 matrices. Okay, so let me call them as, yeah, I don't need to call them anything, but let me just say, so consider this set of 4 matrices, 1, 0, 0, 0, right? 0, 1, 0, 0, 0, 0, 1, 0, 0, 1, right? And it's easy to see that any M which belongs to this space of 2 cross 2 complex matrices actually can be written as A times the first one of these. So let me just write this down. Okay, so I hope you see that this set of 4 matrices forms a basis for this vector space. Okay, and this is indeed therefore a 4-dimensional vector space. Now what we'll do by Thursday's class hopefully is actually identify another non-trivial basis choice for the same space. Okay, because this is a space that will be very important to us, the space of 2 cross 2 complex matrices. Okay, and indeed this is also an example of a vector space. So now we can, of course, you can do a leap of faith from here and say that in fact, I can consider a set of B cross D complex matrices, and this is also a linear vector space. And of course, you can then imagine these. Okay, so now the question is, what is the dimension of this space? So while you think about the answer to that, let me also then jump off to a more non-trivial example, namely the space of square integrable functions. Thanks. Yes, indeed, someone actually wrote the answer on the chat. So the dimension of this space is indeed d squared. Okay. And I hope you can convince yourself that there is indeed a basis of d squared matrices that spans this space, and every element can be written in terms of that. Okay, good. So the final example I want to mention is the space of square integrable functions. Okay. Let me just talk about 1D functions. So think of functions, and of course, those of you who've done quantum mechanics know that these are indeed the wave functions of quantum mechanics, right? So let's think of functions of this form, psi of x, right? Essentially taking you from, okay, for now we can define some interval on the real line, okay? 0 to 1. So x takes values on the real line from 0 to 1. And this function maps you from that to the space of complex numbers, right? So these are complex valued functions. Okay. So these are essentially complex valued functions. And the fact that they are square integrable means that when I write this integral, which is psi star psi, okay, or equally mod psi of x squared, this integral does not blow up. So this is finite, right? So those functions, those complex value functions for which this integral takes on a finite value constitutes a space of square integrable functions. And in fact, this constitutes a Hilbert space, right? Because now you will realize that this is no longer we're no longer talking finite dimensions, right? The function is mapping one infinite dimensional space, or this is a set of functions which is in a continuous variable space, right? So this x is a continuous variable. Remember, everything else that we spoke about so far are discrete examples, right? Which means that there is a discrete set of elements in terms of which your vector space can be written, right? And not just discrete, but finite. So I hope now you can distinguish the dimensionality of the space, or you can identify what one means by dimensionality. It's a question of how many distinct elements do you need to represent all the elements of the vector space, right? And in the case of our d-dimensional complex column vectors, it was exactly d, right? One needed exactly d elementary vectors in terms of which every other vector could be written. So this is a finite dimensional space. The space of 2 cross 2 complex matrices is, of course, a finite dimensional space. The qubit space, which is a special example of this. So, of course, the qubit case, maybe we'll dwell on that in detail. So, the qubit space is basically C2 is an example of is a specific case of the CD space that I just defined for you, right? And of course, the D cross D complex matrix is also finite, but this is our first brush with an infinite dimensional space because this is now a continuous variable X, right? And one cannot span the space with just a finite basis, right? A finite set of elements. One needs an infinite family of functions which will constitute a basis for these kind of spaces, right? And these are indeed the wave functions that we study in a regular quantum mechanics course, right? So these are the wave functions that one studies in quantum mechanics, right? But for the rest of this course, for the most part, we will only focus on finite dimensional quantum systems. So associated with them will be finite dimensional linear vector spaces, right? Okay, so the next concept that I want to define for linear vector spaces is the idea of an inner product. And I will also define it using the Bra-Ket notation. Okay, so yeah, so before I talk about what is a unit vector in postulate 1, I have to define the idea of inner product and norm, right?
Excuse me, ma'am.
Yeah.
Ma'am, so in the definition of the basis for the vector space, can we say that so all these basis vectors will have a unit norm?
So that's a special kind of basis, and I'll come to that, right? So what you're talking about is a special kind of basis called orthonormal basis, right? And of course, we'll be mostly interested only in orthonormal bases. But it's not necessary that these things have to have unit norm or that they have to be mutually orthogonal, right? In fact, what is a precondition is that they must be a linearly independent set of vectors. So I will mention that right away. Actually, I should have defined linear independence already, maybe, but I can define it when I'm doing this. Okay, so maybe I will do that now since you asked the question. So let
Yes,
me,
ma'am.
yeah.
Because
Let me just,
actually that is clear that they are becoming linearly independent. But in fact, with this way of representation, we can have many such vectors. Like instead of that 1, 0, 0, we can have by a factor if we come like half factor if we take out, we can have 2, 0, 0 or 3, 0, 0 and so on.
of course, yeah,
Yeah,
yeah.
yeah, ma'am.
So by the way, there is no unique basis set for a vector space.
Okay, ma'am.
Okay.
Okay, ma'am.
Even if you put in constraint of orthonormality, there is no unique basis,
Yes,
right?
ma'am.
There are several possible bases for any vector space, finite or infinite dimensional, right? I mean,
Yes,
it
ma'am.
doesn't matter whether the vector space is finite dimensional or not. There is no unique choice of basis vectors, even if one puts additional constraints saying that the vectors in the basis have to be orthogonal or normalized and so on. Okay, so let me just conclude. So thanks to Avik, so let me also define what is linear independence. So we say that a set of vectors Vi in a vector space is said to be linearly independent if none of these vectors can be written as linear combinations of each other, right? It's a very intuitive sort of definition. If alpha Vi equal to 0, so I'm going to write it like this: sum over I alpha I Vi equal to 0, if and only if all the alpha I are 0. Okay, so I've written this in a somewhat abstract mathematical way, perhaps. So let me clarify this a little bit. So what do I mean by this? So for example, consider the 1, 0 and 0, 1, right? Belonging to C2, right? So if I were to write some alpha 1, 0 plus beta 0, 1 equal to 0, if this were possible for some non-zero values of alpha and beta, then it means that I can write one of these vectors in terms of the other, right? It means alpha 1, 0 is minus beta 0, 1, right? So this kind of a linear combination being equal to 0 is possible if and only if alpha and beta are both 0, right? I hope you see that. So the vectors which we saw earlier, which were all spanning the different vector spaces that I constructed, right, were all linearly independent sets. You cannot write one in terms of the other. But let me give you one more example. So, okay, so here's a quick test for you. You can answer me by the end of this class. So consider these two sets, 1, 0 and 1, 1 belonging to C2. Okay. Okay, I think with two vectors, it's maybe hard to say this. So let me put a third vector here. Okay. Let me give you this set of three vectors. Okay. Are they linearly independent? So this is the first question. The second question is these two vectors, 1, 1, 1 minus 1. Okay. Are they linearly independent? Okay. This is something for you to think about. So I've given you two sets, 1, 0, 0, 1, 1, 1. Maybe that answer is obvious, but the second one, 1, 1, 1 minus 1. Just let me know whether both these sets are linearly independent sets or not. Okay, fine. So let's move on to talking about inner product now. So before I talk about inner product, I want to talk about a bra vector associated with every ket vector. So this idea of so if I have a vector v, right, if I have this ket v, okay, then I associate with it, this is a straight line with a right angle bracket. So I can think of a left angle bracket, right? And this is what would be called the bra v associated with the ket v, okay? This idea in formally in vector spaces is called associating a dual space to the with the vector space, right? So this is what's called a dual space associated with the so-called primal vector space, right? So what is this association? Again, it's often useful to think in terms of some concrete representations and so on. So let's look at the example of vectors belonging to CD. Sorry, just give me a second. Hello. Yeah. No, it's not. Okay, sorry guys, I should have taken out the phone in my office. Okay, so let's think about this vector space, which is the d-dimensional complex vectors, right? Which are all represented as these column vectors, right? Now, how do I associate a dual with this, right? So the idea of a dual, so let me maybe motivate this a bit more abstractly before I give this example. So the idea of a dual is the following, that a vector belonging to the dual space, so let me say that W is a vector which belongs to the dual space, when acting on a vector in the primal space, gives me a scalar or a number, right? So the dual is something which induces what we call an inner product between two vectors, right? And a concrete way to realize the dual, as in this example that I wanted to show you. So we saw that vectors were represented as columns, right? V1, V2, etc., V sub D. the dual associated with this, or the Bra vector, right? So this is the Bra V, right? Is defined as the complex conjugate followed by the transpose of this Ket vector. Since we have working with essentially a matrix representation of this, we define the dual space via this matrix operation, which is a combination of complex conjugate and transpose. And this combination is what is often referred to as the adjoint of a matrix, right? And it is denoted by this dagger symbol. So let me introduce that symbol also. So this is the dagger of this, right? And of course, these are both matrix operations that everyone is familiar with. So the transpose will make a column vector into a row vector, and then you have to take the complex conjugate. So this is V1 star, V2 star, etc., VD star. So essentially, the Bra vector is a row vector, right? So you've gone from what's a column vector to a row vector. So this is V cross 1, then this is 1 cross D. And so now this idea of an inner product makes sense, right? That the inner product is a way to define a dual space such that the action of some vector in the dual times the action of a vector times the vector in the original vector space itself has to give me a number. So now how will I define this? So let's say that for two vectors, W and V, both belonging to this to CD, which is the d-dimensional complex vector space. Let's say that W is elements are defined as W1, W2, etc., WD. Then how is this inner product defined? It is simply defined via a matrix product. So the more abstract definition is what I tried to give you here, where I said that it is the action of the dual on the primer, right? But the concrete realization of this inner product is simply a matrix product. So this is now a simple matrix product of this form. So remember that to take the Bra of W, I need to write down the corresponding row vector with the entries all complex conjugated. I hope everyone understands that when I put the star, I mean the complex conjugate, right? So V1 star is complex conjugate of V1, okay? Which means if V1 is of the form A plus IB, then V1 star is A minus IB. Okay, I hope everyone is, this is a notation that I'm going to use. I know maybe some people are used to using a bar on top, but for me, bar will mean a complementary binary operation, right? My 0 bar is 1 and 1 bar is 0. So I will use star for complex conjugate. So this is 1 cross D. And then I have this D cross 1. So of course, the rules of matrix multiplication tell me that I must get a 1 cross 1 object, which is a scalar indeed. And so this can be written now as Wi star Vi sum over I going from 1 to T. So this is what defines the inner product for these kind of d-dimensional complex linear vector spaces. So I must say that although I keep talking about d-dimensional complex vector space and I visualize it in terms of this d column vector, actually I'm not losing out on any generality by making this equivalence. So it's a kind of theorem, you can take this as a theorem that every d-dimensional complex linear vector space can be represented in terms of these kind of complex column vectors and vice versa, right? Okay. So this is a concrete way of visualizing the inner product. Once I visualize an inner product, I can talk about the norm of a vector. So the norm of a vector is the inner product of V with itself. It's usually defined as the square root of the inner product of V with itself and is often denoted like this with two parallel lines here, right? So I could put a ket here if you wish. Okay. So note that this inner product is in general a complex number, right? Wi star Vi is some complex number, and I'm summing up a whole bunch of these complex numbers. But now when I take the inner product of a vector with itself, what is this? So the norm of V in this for CD, right? So for this D-dimensional. So this definition, of course, is a general definition, but for this D-dimensional complex vector spaces, the norm is simply square root of sum over I, Vi star Vi, but it's nothing but mod Vi squared, right? And so you realize that the inner product of a vector with itself is a real quantity. Not only is it real, it is also positive, right? And so this square root is also defined to be the positive square root. So this is something which is always greater than 0. In fact, the norm of any vector is 0 if and only if the vector V itself is the null vector in the space, right? Or the 0 vector in the space. In the space of D-dimensional complex vectors, this is nothing but the column vector with all zeros, right? That is the null vector. So the norm is 0 if and only if the vector in question is a null vector, and in all other cases, the norm is positive. You can visualize the idea of a norm geometrically as the length of a vector, right? So the norm essentially is a kind of characterization of the length of a vector. So in real three-dimensional space, the norm would simply be the x component squared plus the y component squared plus the z component squared, which is what you refer to as the length of a vector, right? So the norm essentially captures the idea of the length more abstractly, right? So once you have an inner product, you have a norm, okay? And just to repeat what I said earlier, that any finite dimensional linear vector space with an inner product. What do I mean by with an inner product? I mean, if an inner product can be defined for such a space, right? And note that one has to identify an inner product for the space. Why do I say that? For the space of complex D-dimensional vectors, there was no problem. I could easily define what the dual was, complex conjugate transpose. Then this just became matrix multiplication. This is just a matrix product. But now what if I have the space of matrices? Remember I said the space of 2 cross 2 matrices is a complex linear vector space. What is the inner product for that space? So that's something that needs a bit of thinking. We'll come to that in subsequent lectures. We'll define the inner product for that space also. I just want to reiterate that any finite dimensional linear vector space with an inner product is a Hilbert space. Okay? And what quantum theory tells us is that states, remember this is what we started this lecture with, which is postulate 1, which says that quantum states, so I'm going to now start using the notation ket psi, right, to denote the state of a quantum system. Quantum states are essentially vectors in some Hilbert space H. They are not any vectors, I said, but they are unit vectors, right? So what is the idea of a unit vector? A unit vector is a vector with unit norm, right? And what this means is if I take a quantum state and evaluate its norm, then I'm constrained that the norm of this state must be 1, right? So quantum states are associated with unit vectors or vectors with unit norm in a Hilbert space, right? And the Hilbert spaces that we are interested in, for this course at least, are finite dimensional linear vector spaces with an inner product which is well defined, right? Like in the case of these complex d-dimensional vectors, and any state of a system is a state with norm 1. It's a vector with norm 1. Okay? Questions?
So, ma'am, this will put a restriction on those alpha and beta that we defined initially, like there will be mod alpha square plus mod beta square equals to 1. This condition should hold, right?
Indeed, exactly. So that's exactly what I'm coming to now. Yeah.
Okay, ma'am.
Yeah. Any other questions? Okay, so now let's get back to discussing the qubit state in some more detail, right? So what I mean by state space is essentially the linear vector space or the Hilbert space that is associated with a particular quantum system. Now, qubits are associated with two-level quantum systems. Mathematically, they are associated with C2, which is two-dimensional complex linear vector space, right? So the classic example of a two-level quantum system is, of course, a spin-half particle. For those of you who have done some quantum mechanics, you know that this is the spin space for a spin-half particle is essentially a two-dimensional Hilbert space, right? And yeah, so mathematically, that's nothing but a 2D complex linear vector space. So I know that I can write this. So I can write any arbitrary state of a qubit in terms of a two-dimensional complex column vector like this, right? I know that 1, 0 and 0, 1 form a basis for C2. So I can essentially write this as alpha 0 plus beta 1, where the 1, 0 I associate with ket 0, the 0, 1 I associate with ket 1, right? But what is more now, I said that quantum states have to have unit norm. So this is to be alpha 0 plus beta 1 with mod alpha squared plus mod beta squared is 1, right? So this is what completely defines a qubit for me, that it is an arbitrary linear superposition of ket 0 and ket 1 with mod alpha squared plus mod beta squared equal to 1. So this constraint of unit norm is a physical constraint, and it's a constraint that is related to conservation of probabilities, okay? And we'll come to this when we discuss measurement. That is where this constraint comes from, right? I just want to take another 2-3 minutes to start discussing this geometric structure of the qubit space, right? So maybe just a couple of more minutes. So now let us try to identify. So let me now pose this as a question. So I've told you that a qubit is a two-dimensional Hilbert space, two-dimensional complex linear vector space. So let me say, how many real parameters do we need to characterize psi? Okay. I hope you understand my question. So I know that I can write psi as alpha 0 plus beta 1, right? But of course, alpha and beta are complex parameters, and they must sum to 1. So how many real parameters do I need in order to write down an arbitrary state of a qubit? That's my question, right? So what do you think?
2.
That's because you already know the answer. So you've already done this in some other course, is it? Why 2?
Ma'am, because the overall phase can be factored out, so it won't
Correct.
matter.
Yeah.
And there is one relation between the magnitude.
Indeed. Okay, so maybe I will dwell on this a little bit in the next class, but indeed the answer is 2, right? Now it's easy to see that we actually start with 4, right? So now if I have 2 complex numbers, then that should imply 4 real parameters, right? But I have 2 complex numbers plus 1 constraint, right? Which is the constraint on the norm, right? The norm must be 1. So then this actually becomes 3 real parameters. Now the reduction from 3 to 2 real parameters happens because of the freedom in choosing the overall phase. And this is something I'll explain in Thursday's class. And then we'll see that we can actually represent this in a nice geometric way, that we need exactly 2. In fact, we just need 2 angles to represent the state of a qubit. Okay, so let me stop here. And any questions?
Excuse me, ma'am.
Yeah.
Will you be posting your handwritten notes as well?
Yeah, I do post them on the same folder. If you have accessed the lecture folder, then I also post these handwritten notes there. Right. Yeah. Questions? Okay, what about this question I asked you about the linear dependence? Are both the sets?
Yeah.
The first one is
First
not,
one
but
is
the
linearly
second one will be.
dependent.
Good. So yeah, let me just go back to this. Yeah. So the first one is
Linearly dependent.
Independent.
okay, good. So the answer to this is no, because indeed you can represent 1, 1 as a combination of 1, 0, 0, 1. But what about these two?
They are independent.
How did you show that?
From that, if you take A into 1, 1 and B into 1 minus 1, so we can prove that A and B will be 0.
Indeed, yeah. So you will just get a set of 2 equations from which it's easy for you to see that 1, 1 and 1 minus 1 are in fact linearly independent. In fact, these are the plus and the minus states up to a normalization factor, right? I simply haven't normalized them, right? So yeah, anyway, next class we'll do a few more exercises about normalizing and so on. But these are essentially plus minus up to an overall factor of 1 over root 2, right? And they are indeed linearly independent. So they constitute another basis for the qubit space. Okay. All right.
Ma'am?
No further. Yeah.
Ma'am, there's a doubt. So, ma'am, when I was reading this section from Nielsen over the Deshu algorithm, so there was this term called -1 to the power fx and x get. So
Yeah.
I couldn't understand that thing. Like when we did in the class, we directly brought fx and
Correct. Yeah.
and we're doing
Yeah.
that.
Yeah. So I didn't use that more abstract notation. So something extra that you're asking me here. So let me write this out in the end. So what you're saying is that this, what I wrote as either 0 plus 1 or minus 1 by root 2, right? They actually write as 0 plus minus 1 to the f of x 1 by root 2, right? Something
Yes.
like this. What does this mean? So now when f of x is 0, this becomes 0 plus 1. And when f of x is 1, this becomes minus. So this is a compact way of writing down the different cases that I wrote down in class on Friday, right? So this is just a more compact notation to write down, to say that actually the value of f of x feeds into the relative phase, right? And
True.
yeah. I hope
So
this
that means
clarifies it.
they're assuming some form of fx here, but when we did in the class, we didn't assume any kind of, any form of the fx, right?
No. All that they're assuming that it's binary valued, no? That
Yeah,
f of x is either 0 or 1. They're still not
Yeah, but-
assuming any form for f of x.
Yeah, I mean, in the same thing, like we didn't define like what the function, but yes, it was a binary
Correct.
form. But
Correct.
yeah.
Yeah. That's all. Yeah. It's the same thing. It's the same thing. It's just a different, it's a more abstracted way of representing it. That's all. Okay. We'll also do Deutsch in this form, right? Where we will abstract out the phase information. In fact, you can write this as something like f of x XOR f bar of x or something, right? To say that actually whether the function is constant or balanced is what decides what this phase is, right? So in some sense, it is f of 0 XOR f of 1. So I can actually write the final state in the Deutsch algorithm like this, right? The -1 to some phase. And what is that phase? It is simply comparing f of 0 and f of 1. And if f of 0 is the same as f of 1, this gives me the plus state. And if they are different, then the XOR of two different bits is 1, right? And so that gives me this part. Okay?
Yeah.
So in fact, this would be the more abstract way of representing the Deutsch final output. Okay. Any
Okay,
other questions?
thank you.
Yeah, sure. Good. I'm glad people are reading Nielsen. Any other questions, guys? Okay, so then I stop here. I'll see you on Thursday, and I'll discuss what I had hoped to cover today but do not have time, which is the block sphere, the geometric representation of the qubit state space. Okay? Yeah. So let me stop. I'll see you all on Thursday.
Excuse me.